Good morning or good afternoon, depending on where you are now. This is Eric Zhang. I'm a professor from the Department of Civil and Environmental Engineering, the Hong Kong University of Science and Technology. Today, we are very honored to have Professor Mohammad Ghidawi to deliver a presentation entitled Smart Urban Water Infrastructure and Beyond. Professor Ghidawi is a chair professor in the Department of Civil and Environmental Engineering, the Hong Kong University of Science and Technology. He is a fellow of the Hong Kong Institution of Engineers and also a distinguished fellow of AAHR and the vice president of AAHR. Professor Ghidawi is the chief editor, a Journal of Hydraulic Research, and also associate editor of Journal of Hydraulic Engineering and associate editor, Journal of Hydro-Environmental Research. Professor Ghidawi is also on the editorial board of a number of reputed international journals. So without further ado, let's welcome Professor Mohammad Ghidawi. So Mohammad, please.
Yeah, thank you. Thanks, Eric. Thanks, Shanhao. Thanks, Rebecca. Thanks, everybody. And glad to see a good number of you attending here. I just asked about the background, and I know it's more about management, so I will promise you to skip any slides about equations here. So I'll focus more on what the problem is, what's the essential idea or technology that we developed or we're developing now to deal with it. And I will show you half of the talk will be about where we are applying it currently, both in Hong Kong and in other cities around the world. This technology of came from a theme-based project that we got about 7-8 years ago, and it was about $40 million Hong Kong. And the problem we were trying to tackle is to deal with the challenges related to water supply systems, defects in water supply system. I think when I mention that, most of you will immediately probably think of leaks and bursts and so on. And those accounts for a lot of water losses. Worldwide, it's probably 30 to 40% of the water that goes into your system on average never makes it to the consumers. The financial values of those is that direct cost alone is about $50 billion per year. Other defects can be malfunctioning devices, as we will see, can be blockages in pipes, as we will see as well. So we got the money, and then we tried to find how we can detect this. And what we were hoping for is for a long range, non-destructive system, and that is we should not stop the water usage, as you test, and it should be one of those quick ones. It should be long range, it should be cheap, hopefully, and does not stress the system in any way. So we are actually implementing it here on our campus, and we go and do the testing, and nobody in the campus knows that we're actually testing, and that's what we mean about non-disruptive. So after a few years of struggling, with a solution, after we get the money, then reality hits, and you have to come up with a solution. Then it dawned on us is, what do people in other fields do, like medicine and so on? And one of the things that we came across was time reversal, and I'll share with you the physics of it, and I'll show you some videos of it. I will not show you the theory, just some videos, and then I will tell you how we used it then to work on water supplies and also pressurized sewage systems. So I need to get some help here. Yeah, so my list here is, we will try to look at the evidence or some videos essentially about what is time reversal, and then I'll show you some of the applications of it, and I will finish up with moving to imaging. We're actually now moving to the state where we're trying to turn this into an imaging like what you do with the medical system of ultrasound, and have a quick closing remarks. So first, really what's interesting to me in academia is what is this idea of time reversal? We all know waves, and if you drop a stone in a pond, you see the waves emanating radially, something like what you'll see here. That the black dot is the stone, and you see waves emanating radially. Now, what time reversal says is that if you measure the pressure signals that is generated by the wave, like what you see there in these curves, and if you time reverse them and make them to be the source, and then you send them back, the waves will focus on their origin. They will tell you actually what the source is. So meaning I'm sitting here in a room and I'm talking, if you have pressure sensors in a couple of locations, you measure my sound, you reverse it, you can actually tell where I'm sitting. Okay, now for us, this idea, once we saw it, for us, the source, the black dot, can be a leak, can be a blockage, can be a burst, and so on, and we will see how we use it. So it's a nice idea in principle, but how does it really work in experiment? Here is a video of a stone that will be dropped into a big pond, and the people who did the experiments are just measuring here on the right-hand side. You see they're measuring the wave height or the pressure effectively. Okay, so nothing new to you there. I'm sure all you, the audience, can follow that. Now they time reverse, and here's the interesting part, that they send the waves after they measure them, they send them back, and you will see we're speeding it up here to save a bit of time, but you'll see the waves focus back on, if all works well, they focus back on where the stone is. Okay, see the blip there? So the wave actually tells you. So if you didn't know, if you're measuring, you happen to be measuring, you have your pressure sensors, you're measuring, and you go back and play these pressure signals backwards, you'll actually tell whether something dropped there or not. But another thing that I like to just mention to you, you see you get the peak there for the stone, but you see all these waves in the background. These waves in the background is what we call, basically they are caused by, we call them side lobes, and they are caused by the fact that we are not measuring everywhere, or you can, on the walls meaning, or you can measure longer. That's how you could reduce those, because if you don't, they can actually give you fault defects. They can give you fault sources. So we try to minimize them, and lots of the research is about minimizing those. These are experiments that were done in Paris by a key person who leads a lot of this research in physics, Matthias Fink. You see here, again, that's the forward problem, dropping the CN tower and water again and sending waves. Now you measure them, you reverse them, and you get back a picture of the Eiffel Tower. So again, what's really interesting here is that these wave reversal, time reversal, can actually give you a trace of complicated shapes. Means you can also use it to image, something we are trying to work on right now. I'll skip this. This is acoustic. So I showed you gravity waves. We can try to show you acoustic waves, like what I'm doing now. These is acoustic waves here in the room, but of course you're hearing me through electromagnetic waves. Again, they are measuring along these dots here. Now I'll take you to the time reversal stage. So now they measure these sound waves, they send them back, and if all goes well, they will refocus back on the source. Okay, so again, if you bear with me for a minute, so gravity waves therefore are time reversible. Acoustic waves, as you will see in a few seconds, are also time reversible. Let's see. All right. Okay. But you notice that the diameter of the refocusing like what I showed you here, sorry. Yeah. The refocusing does not necessarily tell, the size of the refocusing is not necessarily the black dot. To get close to the black dot, you need larger frequency. And that's why when you go to medical imaging, they use ultrasound. Ultrasound then can give them better and better resolution. Means making that circle smaller and smaller to basically trace back the dots that you're trying to find. So now, this is a video again of time reversal of electromagnetic waves. Therefore, they are, we can show they are, and I'm going to skip this, which means this technology is also used in wireless communication, time reversal. This is for elastic waves. You see there is these figurines, and they're going to send a source. Okay, the source is being sent from this figurine. It's being recorded here. You're going to take it and time reverse it. And when you do so, if time reversal works, only the figurine that where it was sent actually will fall down, because that's where the peak of stress is. Similar thing happened here. So again, the stress wave was initially sent from here, it was recorded there, and when it was sent back, it only focused back on the figurine or the location where it was sent. So these waves are also time reversible. Interestingly, this is why the title says beyond. There are attempts to use it in concrete, also to find faults in concrete. This is a concrete structure where they send waves from this location. They measure at these outside, and then they time reverse, and again you get the refocusing back of these waves. So for them, for example, the source therefore could be a sudden crack in a structure, and so on. Many now medical devices are actually on the basis of time reversal. So one of the ways to use it are for kidney stone. And what they do is they send a test wave in the left-hand side here. And the test waves will, of course, reflect strongly from the stone. They measure that. And once they receive that signal, they time reverse it and amplify it with a lot of energy. And the energy will then focus on the stone only, like that pond where the waves focus back on where the location of the stone, right? One of the early experiments was this in water application was actually in the Mediterranean Sea. And it was, I think, about 10 kilometers, and then later on about 30 kilometers actually in what we are seeing here. So again, they are sending acoustic waves and they are measuring it about 30 kilometers away. Then they time reverse it and send it back, and you get very good refocusing. We did a test in pipelines in Hong Kong, in a real pipeline, where now our source is we let the water out from the pipe and we measure at two locations. So this is where we send it, this is where we measure. Then we get the two measurements and we time reverse them. And we'll see when we do that, actually the waves again, they reverse and they tell us the location of where we send our waves. So this is a field proof for water supply that this idea works for us. And we know from the theory, we know from the equation that they should work. And we have now a number of publications on this. We also did this in our experimental facility, and this is over a range of about, and this one I think is about 36 meters. So again, we send a pulse wave like this. We receive it on the other side, and it's quite distorted and dispersed. So this is what we send. This is what we receive about 40 meters away. Why? Because here we're sending high frequency. High frequency, I think in this case, was about 30 kilohertz. When you send 30 kilohertz on a pipe, it's like you speaking in a tunnel. You're going to get a lot of echoes. And these are the echoes you're getting, right? And now when we time reverse it, we send it back, and it will refocus back, and it tells you where the source is. But again, you get the side lobes. So the main peak here is the equivalent of what you saw on this pond. The side lobes is the equivalent of this. If we want to again suppress these, if we measure at more points or we measure longer meaning here we're measuring only for a fraction of a second, right? 0.05 seconds. But if we measure for maybe a couple of seconds, we will reduce these lobes and the energy will focus more on where your source is. Okay, so now, as I said, I promised to skip the math. Now moving on to the applications. We actually have, just before we do those, we actually have 5 patents from this so far. And we have a startup here in Hong Kong using this technology. And our group also was in Geneva for the technology competition, and they brought back the silver medal award, okay, with working with our colleagues here in the drainage service department. So this is the project where we went and we applied it to, and then we competed in Geneva. We are applying it with the drainage service department and the water supplies department, who have been very helpful throughout. And currently, we actually have a project with the Hong Kong airport. So our instrumentation is at the Hong Kong airport. And in that case, we're helping them use WAVE to help them decide which pipes are ready to be replaced and which pipes are still in good condition and we could keep them. All right. So one of the applications we did was actually in Hong Kong Disneyland in Penny's Bay. And they had initially, in this case, they actually measured data. They hired some outside company that collected real-time data for them. And then they gave us a project where we used time reversal to see if there is. So we have essentially the wave signals, and our job was to time reverse them and see if we can find anything wrong with the system. And immediately, it seems we spotted that there is potentially something wrong with the pump, that there is a lot of vibration, and we detected that probably one of the air valves was not functioning well. This is for sewage system, but it's pressurized. Okay, so of course we needed to go and verify. We contacted our colleagues in drainage service department. We said, we think you have a problem with your air valves. They may not be functioning very well. So we went to the valve chamber. This is our group. We opened it up, and some of their engineers, and in fact, it was flooded, and that's why it was not letting air out. So there was a lot of air being trapped in this system, and that's not the way it's supposed to be, of course. Now, for the pump, it was easy because we went back and said, okay, well, we think it's vibrating. This is one location of measurement in a couple of kilometer pipelines. And the reason we can do that is because these waves travel at about 1 kilometer per second. So that means a 2-kilometer pipeline, you could sample them in about 5 to 6 seconds. And so these are really as quick almost as your ultrasound in the medical business. But of course, here we're doing further because this is a long range. Now, if we suspect that the pump has something wrong with it, we put accelerometers and we measure it directly. And in fact, when we put it in a spectrogram, we identify some frequencies that are expected to be there. This is due to the rotational speed of the pump, but there is these higher frequency at 400 to 500 hertz. And those we reckon they had to do with axle twisting and vibration of the pump. Now it has been taken off and checked, and we understand, yes, there was something wrong with it and had to be replaced. The other thing we found is, of course, we measure the wave speed, and we found that the wave speed is excessively low, meaning that there is a lot of air in the system. Again, remember I told you the wave speed should be about 1,000. We're measuring wave speed of about 170. That to us means there is a lot of trapped air in the system. And of course there was, because the air valve was not working properly. But what it means is if you find your wave speed drops to this low level, you're trapping lots of gases. And trapping gases can cause corrosion and eventually leaks. So this is usually measuring the wave speed is a really good thing to tell you about whether your system is running properly, it performs, and whether it's going to have potential health issues in the future. Now, another project was this is in Stanley, in a nice little town in Hong Kong, well, little, not if you're in Europe or another place, but if you're in Asia, it's little. They suspect there is a sewage leak, and it's in coming out to the streets of this village. And we were asked to see if we could localize it quickly. So our group went and did again the time reversal testing on it, and we were able to localize it within a meter, within a couple of meters, and that was all what was needed. And in fact, it was fixed. So this is the sewage leak, and it was found and basically fixed and repaired. Now I'll move you on to the application in water supply systems. One of the applications was actually a test application. This is a system where we got from our colleagues in the water supplies department, and it's in the real water system in Hong Kong. Again, we went and we sent a wave and we measured. Again, the measurements is just here. You see, it's a couple of seconds really. We time reverse it and you get peaks. So we get sources, essentially. We're telling us there is something happening here, there is something happening there at all of these locations. So the first one, the interesting one, was we reckoned that there was some line going in here. Maybe there is another pipeline that was not in their maps. We contacted our colleagues in the water supplies department, and they were not so sure initially. Then they went and checked the old maps. And in fact, it did show that there was a pipeline connected here, but it's no longer in use, but the wave was finding it. This is a simulated leak that we actually introduced, so we are able to find that. This is consumer connection. You see this building here. So, sorry, there is a building there and there is a consumer connection. So the wave again finds that pipeline, that junction. Another interesting one was the PRV. When we talked to them initially, and we've been testing for quite a few years, we thought the PRV was there, but then we were told it was taken off commission, and it was indeed for some time. But when we did one of these tests, we realized that it seems to be back online. So we contacted them, we said, is your PRV back online? And again, they said, not so sure. We need to check with the mechanical people. And indeed, after checking, it was back on. So the message here is that it's not a leak finder. It's more of a general health assessment. Like I showed you the pumps or the sewage, like I showed you the valves. You can find junctions. You can find whether PRVs are working, and if they are working, whether they are working properly or not. This is another test in Yonglong. This is a test where it's quite critical to find out whether a leak really exists or not. We've done a couple of years ago because it's under, I think, an 8-lane highway, this pipeline, and they really don't want to dig for the sake of digging. They want to make sure that it is in fact there, and these are the results we got from it. We work very closely with our colleagues from Perugia, Professor Bernuni and Professor Menaconi, and they do a lot of the transient testing also in Italy, and we got the data and applied time reversal to it, and we get, again, in this pipeline system, we're able to detect air blockages and leak in the system, which our colleagues already actually found there and helped our colleagues Silvia and Bruno in Italy. This is again tests done by them in the city of Milan. It was really a nice test that they've done where they generated the wave by tripping a pump, and I think the measurements were 5 kilometers away. So again, I like to emphasize here that these waves, if they are low frequency, meaning anywhere of the order of tens of hertz, they travel kilometers. In this system, they travel up to 10 kilometers. So they can actually give you long range measurements. They were able to detect a bunch of leaks. And again, when we did the time reversal, we were able to localize those leaks that were bunched up in that area. This is an interesting one in Hong Kong. And again, this is a message I like to pass. There is a lots of move to say, you know, like, what's a smart system? I think there is a belief that you buy lots of technology, lots of sensor, you put them in a system and it becomes smart. I like to stress here, that is only the beginning of making a system smart. That is the basic infrastructure you need. But now you're going to get signals. And when you get signals, you really need to develop ways to process those signals and squeeze out or extract essentially the information from those sensors. So in this system that they had in Hong Kong, they got these sensors and they were giving them pressures in real time. And it's fun initially, I think, for engineers to see it. But once they see something bizarre, they get agitated because they want to know what's going on. And same as a human, when you go to a doctor and they see some signal, you get a bit stressed. You want to know what it is going on. And engineers are no different when they see it about their system. So at 4 o'clock each day, they were seeing a drop of pressure of about 10 meters. We happened to be in their office one day, and in fact, they called us, and we went and looked at the screen, and this is precisely the signal you see around 4 p.m., a drop in the signal, and that's from different sensors, a drop of about 10 meters of pressure. And the question is why? So we took it and we used time reversal. This is where we had the measurement at the 2 green dots. We send it back, and when we send it back, this is an our model. We got a model of the system, and let's see what, and observe with me. The idea is where the waves meet, where they peak, is where the source is likely to be. So if our time reversal works and works really well, then the source should be at that location. Now, again, when they did, sorry, I need to get back here. So when they did look at it, in fact, there was another truck that comes from another department. There is a fire hydrant at this location. This truck comes in, opens this fire hydrant, and it comes around 4 o'clock each day, fills up the tank of this truck, and they go away. I think they're using it for street sweeping. So there was no leak in this case. There was no theft. There was no burst, but that's what happened. So again, if you happen to have sensors you're measuring there, it's good. You see these signals. But if you don't have the proper signal processing, it's difficult to know what is happening. It becomes, frankly, more of stress rather than a solution. Now, this is another project in our university. We have a sprinkler system in our university, and they suspected there was a big leak happening in the system, and it has been suspected for about 10 years. And in fact, at one point, they had a contractor who came in and essentially thought he located the leak. And when they dug down about 1 meter in Hong Kong, they did not find the pipe, let alone the leak. So the maps were wrong. And this is, again, another thing, as I talk to practitioners, colleagues, engineers, and they say, how do I make the pipe system smart? I say, one thing foremost is keep good data about your pipes when you put them in now in the ground. And these days, there is really not much excuse not to do that with BIM being around. So we should keep good information about at least the geometry, the material property, the layout of our pipes, and so on. The other thing that I'll talk in a minute, we should also make them accessible. So technology like ours or developed by others can also be, integrated in these very important infrastructure. So what we did, again, we found the leak using time reversal, and you see here there, I don't know if you see it, there is this hole there, and that's where the leak is. And because the pressure in Hong Kong, we drive our water using reservoirs and mountains, so the pressures tend to be very high, and therefore even a small hole will leak a lot. And the leak here, when everything was operational, is about 3 liters per second. That's a lot of water just from one leak. You can do the computation and you find it's tremendous, right? 3 liters per second. Now, the other thing, though, when we took the pipe and cut it out, you see there is all of these other areas. They are not leaking yet, but they could become leaks. But our signals that we send could not pick them up because we were sending tens of hertz waves. When a wave is 10 hertz, the wavelength is about 50 meters. Waves of about 50 meters cannot give you the resolution to image something of that nature. They can image a leak because a leak is a strong signal and it also creates turbulence around it, but they cannot scatter from something very small. So if we want to measure, if we want to see something like this, you know, of a few centimeters diameter, we have to send waves of the same size as that, right? And if we send waves centimeter, we need to send tens of kilohertz, right? So we need essentially to move to the idea of imaging. So we tried to test this then initially numerically in our computers. We went and said, what happened if we put a wall thinning in a pipe of a couple of millimeters? Or perhaps the defect could be just a change in stiffness of 10% from a pipe wall, maybe because of age, or maybe because initially when you bought the pipe, it actually have some localized, defect in it and you're not aware. And we also put a small defect on the outside of the pipe, that is between the pipe and the soil. And our numerical results show that, in fact, that is, if you send waves at about 30 kilohertz to 50 kilohertz, you can actually image these. You can see them, see their size and scale. And the idea here is, can we see these faults before they become real faults? And if we can do that, we can plan our management better. You as managers can decide, should I act on it? What is the cost if I act, and what is the cost if I don't? If it's a pipe that is not important, that is out there, and it's going to cost you lots to do something about it, you can say, I'll just wait for it till something happens, I'll deal with it later. But if it's a critical pipe in a city, then you'll probably be more likely to say, we need to really look at this problem, immediately and solve it. Now, we tested this in the lab. Then, of course, after this, we put a small blockage here of 7 millimeters thickness and 97 millimeters length, and we were able to image it, okay, using waves. Now, then we went to the field. This pipe system here is about 40 meters long, 36.5. We send waves from this location, and then we measure actually at the same location, again, high frequency waves. And what we were able to do is, through this at high frequency, we can see actually the pipe wall. You can see the junction, a good image of the junction, a good image of the other two junction. And we inserted here a small magnet inside. We intentionally dropped it there. The magnet is here, and we are able to image it as well. So the idea is actually we are moving on our way towards something that is hopefully will be the analog to ultrasound, to actually image these pipes from a single point. And so far as I can show you, we're measuring 40 meters. So, but we can change the direction of the transducer and measure 40 meters on the other side. So at least up to now, we can do this at a range of about 100 meters. But all of our target now, we're doing research, and our target will be to do 200 to 300 meters each way. So that means you need to have these equipment scattered every 200 to 300 meters. But why it's difficult now to do this in any pipeline system around the world is, to do this technology, you need to put transducers. We need to be able to insert transducers into the pipe and send waves. Okay, there is no access. We never built pipelines to be that accessible. But so what we did in our group, we developed a robotic arm where it's able to translate inward into an access point, and you can take the data and then withdraw it. Remember, you only need to collect this data for a couple of seconds, maybe. Therefore, the insertion will be a minute or two. It just goes into the water column and you withdraw it, and then the rest will be analysis. Interestingly, also we tested this and to see if a loose, if a stiffener here, if you can localize a stiffener in the pipe, and in fact, you see you get, when we do the imaging for this or time reversal, we find the source, which is a leak, and we find another peak, and that peak is actually due to the stiffening of that pipe. So you can find stiffeners, right? You can find junctions, because junctions have different stiffnesses than the rest of the pipes. So you actually can find, and you can actually find if it's loose or not. Because if it's loose, it's a place where you're gonna get leaks happening from it. This is a magnet, again, that we put into the pipe. We've just shown it to you here, and then we insert it into the actual pipe system, and we test it. And again, we are able to localize it and image it. This one here is actually a piece of bitumen that we extracted from a real pipeline, and we tested it again. We put it underwater and tested it, and you can detect its presence and actually localize it as well. And in Hong Kong, a few years ago, we had incidences of this bitumen, because there is about 200 kilometers of pipes that still do that, and these bitumen is essentially getting sloughed off. So this technology, we hope, can help us localize these problems and deal with them until they replace these pipes, and that's the plan. And Hong Kong will be to replace them. So this will be my last slide. Essentially, we did prove TR both in the lab and in applications. What we found about it is that it's high resolution, it's noise tolerant. What it does, it gives the maximum SNR. It's robust in terms of applications. It's tolerant to modeling uncertainties. So when you use a model, it's actually takes a lot of beating to essentially throw off the focusing point. No model is needed. So sometimes you can actually get around using models, provided that you can measure continuously, which is something we advise, water utilities to do, is with these sensors, measure regularly, and then it's much easier. It's much easier to tell changes in a system than if I come fresh with these equipment and you tell me, okay, go and analyze my system. I think you all know that. When you go to a doctor, if the doctor knows you and you've been going to them regularly, it's much easier for them to detect if there is anything that is different about you. If you go to a different city and you live in a new city, you go to a new doctor, it takes them time to actually find out your ills. So our systems are also breathing, they are living, they are dynamic, and we really will do better. Their costs, they care. I mean, there is a lot of money that goes into them. They are important for our economy and so on. And it's good to really keep good checks on them. And good checks means monitor them regularly, like we go to see doctors regularly if you want to keep good health. That's all I got to say, and I'm happy to look at any questions you have. Thank you very much.
Yes, thank you very much, Mohammed. A very wonderful presentation. So, for the audience, any questions?
Okay, there is a question where we able to simulate in 3D. The answer is actually our testing in the high frequency is done for 3D. Our model, we are building now currently a model for 3D. Now, 3D meaning we only need it if you want to tell where a defect, not only where it is in terms of axial location, but where it is in terms of the azimuthal location. So yes, we're developing that. Thank you. Thanks very much, Enrico. Any other questions, friends, colleagues? I hope it was clear enough.
Yeah, any more questions? Okay, if no more questions, I will transfer the mic to Professor Townsend. Associate Dean, Business School.
Okay, there is a question. There is a question coming in.
Yeah. There's another one. Yeah.
Yeah. Would you be developing algorithm with the use of AI to advance the researching? In fact, we're writing a proposal at the moment to combine the physics with machine learning AI to see if we can do better. Now, again, that can only happen. I mean, I hear what we want to do is physics informed. We cannot, and I don't advise it, to throw away physics. We learned in engineering. I mean, in engineering, especially in civil engineering, we're very good at using data to turn it into knowledge. And we've done that before machine learning. I hope I'm not insulting my machine learning AI friends when I say that. So engineers have been always not afraid to combine data and extract knowledge from it. AI to me and machine learning is just a much more efficient and better and quicker way to do all of these. But we should not, therefore, throw away the physics that we learned and replace with AI. One of the reasons is we never have enough data. In fact, as I told you, most systems these days, it's very difficult to even collect one single data if we're going to go high frequency, let alone big data. So we're going to be in civil engineering and infrastructure, we're going to be most of the time, even if we do better, even if we move on with the times and make them accessible, we're going to be in kind of some data, and we need physics to combine it. Now, to your questions, in fact, in our lab, of course, when we combine it with the physics, we find a huge success. If we don't constrain machine learning with the physics, we get because wave problems are not easy problems for these things to learn. So we have actually a little paper on that where we collected, where we used simply data and we trained it and we tried to see if it learned the wave equation, and it didn't. But once we constrained with the physics of wave equation, then even when we throw away some of the data, it actually converged and gave us good results. Thank you, though, for the question, Ulrich. I think there is more.
There's another one.
Well, again, I'm not really a user of Internet of Things, I guess, but what we do is we are designing our own system here on our campus. I mean, I guess we are in a way, but we're designing our own system where we are collecting real-time data. And we just got a project about a year ago from ITF here in Hong Kong to turn actually some of these technology that I just discussed with you into a real-time, hands-off thing that we hopefully can sell as packages in the future. So we are developing whatever the needed technologies that we do. We have in our group of students, we have civil engineers, we have mechanical, we have electrical. So together we work and develop what we need. All right, I think that seems to be all the questions. So back to you, Eric.
Okay, thank you, Professor Mohammed, for your wonderful lecture. Professor Mohammed introduced the TR research and its application in water infrastructure. I hope we all can do further profound thinking and research in the light of your views and ideas. Okay, the webinar is over now. Thank you for your participation. Thank you for Professor Mohammed again. Okay, wish you all the best. Okay, thank you. Bye.